So I want to talk a little bit about QoS concepts. Before we actually get into the config work here, we want to have a basic understanding of QoS, the different parts of QoS, what we can kind of do with it, so that when we get to the config section, as I explain different things, it sort of makes sense because you know sort of at least a little bit of the background of the features here. So in the wireless portion of the lab here on our 4500s, on our 3650s for wired QoS, and actually any QoS, one thing to note is that QoS is enabled by default. If we come from the previous version of the exam where we worked on primarily things like 3560 series switches, or people used to 3750s, or many of the other Catalyst switches out there, you actually had to turn on QoS on those. Here, it's on by default. I don't even know if you can turn it off. So it's always running by default here. And the first concept, now that we know that it's running, that we want to talk about here is actually classification. So classification is basically looking at the traffic and sort of identifying what it is based off of a lot of different avenues so that we can do something to it. So we're looking at the traffic, trying to identify it so we can take some sort of a QoS action on it. And we have many different ways to identify different types of traffic. So let's talk about just a few of the possibilities for classification. One way that we could do classification would be through the use of an ACL. So we could write an ACL, and any permit statement in the ACL would match traffic. So as traffic is flowing through an interface, we can have an ACL looking at the traffic to either match it or not match it. So that's one real common way that we might do classification, especially in the wireless lab here. But we have other ways. We could just look at what VLAN the traffic is in. That's another way to classify the traffic. Or we could do something like, what protocol is it? Many switches support a feature called NBAR, network-based application something, and it allows you to, it does deep packet inspection. Like when we run on the wireless side, AVC, Application Visibility Control, it actually uses NBAR for that. So you can actually have it detect the protocol in sort of a dynamic fashion and identify it that way. Or we can use things like QoS markings. So there can be markings directly on the traffic itself, and we can just use those markings as a way to classify this traffic. So we have a few different tools. Probably, again, what we'll use most of the time from a wired QoS perspective would be ACLs or QoS markings. We might use VLANs. I don't know that we're going to be able to use NBAR on the wired side of things. Absolutely on the wireless with AVC, we will be able to. So we're going to focus mainly on ACLs and QoS markings on the wired side. And when we get into wireless, we'll look at a few other tools that we have there. But that'll be in a separate set of videos. Okay, so many ways to do classification. Now I want to actually zero in on this marking part, because oftentimes what we're going to do on the wired side of things is once we classify it, if we don't like its markings or it doesn't have markings, maybe they're all just at the defaults there, we might want to place markings on the traffic. So let's talk about marking. On our traffic in our lab, we have two main categories of QoS markings. The first one that we have is, well, it's Dscp, but it's a layer 3. Our layer 3 marking that we primarily use is Dscp, or Differentiated Services Code Point, I think is what it stands for. This is in the IP header. So all IP traffic has this, whether it's IPv4 and IPv6 has this as well. And our values that we have are numerically 0 through 63. So we have 64 individual values that we could mark on a piece of traffic to then do something with. So every single marking could technically get some little bit of a different treatment somewhere in the network. Now, I don't know any QoS policy that actually relies on 64 different markings. Usually we're just using a handful of markings, but Dscp, an alternate layer 3 marking, this is our biggie right here though. An alternate layer 3 marking is actually IP precedence. This is also layer 3 in the IP header. And the values here are 0 to 7. And both, actually, Dscp and IP precedence are in the exact same spot in the IP header. There is a 8-bit field. Let's see if I can make 8 bits here. Called the type of service field. IP precedence are the 3 most significant bits. That's the IP precedence, and so 3 bits means we can have 8 different values. That's the 0 to 7 there. Dscp is the 6 most significant bits. And so IP precedence is actually a part of Dscp. So we have, it's just 2 different ways of sort of looking at the traffic. Obviously Dscp having many more bits allows much more granular policies than IP precedence does. But if you ever see reference to IP precedence, it's that part of the IP header. It's the first 3 bits of the Dscp field. It's always there if it's an IP packet, but by and large, if we're talking layer 3 markings, we use Dscp. Dscp really is our standard marking of choice in our both wired and wireless networks for policies. Now we'll talk about some other markings that you might use too, but at least on the wired side, DSP heavily favored here. Okay, the other marking that we have is Qos, class of service. This is a layer 2 marking. And again, we're talking wired, so we're not going to talk wireless layer 2 markings. So on the wired side, Qos is layer 2. This is in an 802.1q tag. So if you think back to when we talked about trunks and 802.1q encapsulation, how does that work? Well, basically the 802.1q tag is supposed to say which VLAN a piece of traffic is assigned to as it flows across this trunk, which supports many different VLANs. An extra field in that tag is the class of service field that we can use as a QoS marker. Much like IP precedence, it's a 3-bit field, so we have values of 0 to 7. So oftentimes IP precedence is used as sort of a corollary marking to Qos. You know, they try to match up IP precedence and Qos values if you want some sort of symmetry there, but that's something that we don't technically worry about so much in modern day networks here. It's important to note that it is in the tag value there. So when you think about Qos, you always remember that, well, A, it has to be an 802.1q trunk, but B, this needs to be tagged, which means we don't get Qos on a native VLAN. If you remember, native VLANs do not have an 802.1q tag. They're tagless, which means on that particular VLAN of the trunk, we don't get a Qos value where we will with every other VLAN, unless you're doing something funky like tagging the native VLAN with that global command we talked about back in that video. So the thing with DSCP is we always have it. As long as it's IP traffic, we always have DSCP, every single link, no matter what. With IP traffic, with Qos, sometimes we have it. Just depends on if it's trunk link or not. Is it a native VLAN or not? So that's another reason why DSCP is so heavily favored, is because we can always count on it being there. And so regardless of the port or wherever we're trying to apply a policy, we can always apply a policy on DSCP. We can't always apply a policy on Qos because Qos isn't always there. So those are our common markings that you're going to be dealing with. Again, DSCP is by far the biggie. Maybe you do something with Qos. We used to do more Qos in the old version of the lab, but Qos is really sort of falling off as something that we really build policies off of. Okay, so those are our markings. Now, I want to focus in a little bit on DSCP markings, because what you might find with DSCP is that there are 2 ways to identify a DSCP marking. There's the numerical value of 0 through 63, which is what we commonly use. But we also have this marking called a per hop behavior. And they use letters and numbers to denote numerical values. And you might see those, especially in the running config, or in show commands. Oftentimes what happens is we configure DSP values, we might configure it in the decimal form, but when we look at a show command or a run, show run command, it'll convert it to the per hop behavior. So I want you to know how to translate between decimal and per hop behavior. So if we look at the per hop behavior, there are really 4 types of per hop behavior notations to know. And then they will translate to a numerical DSCP value. So the first per hop behavior we'll talk about is called default. And this just translates to a value of 0. So another way of saying DSCP 0 is saying a marking of default, the default marking for DSCP. Another per hop behavior is EF, or Expedited Forwarding. This maps to a DSCP of 46. 46 you might note as our voice audio marking, our standard voice RTP marking. So 46 is equivalent to the per hop behavior of EF, or Expedited Forwarding. So those are our 2 one-to-one mappings where the per hop behavior has just one value. The next 2, we have an equation to follow. So we'll talk about CS, and then it'll be a number after it. CS stands for class selector. So the math here is it's just going to be 8 times the number is the value. And so if we have, say, we'll do CS3. So we would just take 8 times 3, 24. So CS3 would translate to a numerical value of 24. CS4 would be 32. So it's just 8 times the number. And then we have an assured forwarding class. Is going to have 2 numbers after it. We'll call it XY. And the math there is just going to be 8x plus 2y. So if we have something like assured forwarding 41. And the way that these 2 numbers, the significance of these 2 numbers is this is the class and this is the drop probability within the class. In general, with these numbers, the higher the number, the better treatment it should get through the network. The only sort of difference with that is when we get into the assured forwarding classes. So we can have this second number, y, is a value between 1 to 3. So the first number higher is better. So AF 40 something is always better than anything AF 30 something is always better than anything AF 20 something. But within a given class, the lower the number, the better. The lower the number, the lower probability of the traffic being dropped. So an AF 43 has a higher drop probability than an AF 41. You probably won't have to worry so much about that. Most of the time in the lab, they just tell us what markings we're supposed to use, or we just use some pretty standard markings to begin with. I just wanted to throw that out there. So AF 41, the math would be 8 times 4 plus 2 times 1. So what's that? 32 plus 2, 34. So there are per hop behaviors, and there are the either corollary numbers or the equations to come with the numbers. And so if you see any of these per hop behaviors, just know how you can translate it to the appropriate numerical value, and you should be able to sort of figure out vice versa as well if need be. So that way, whichever way you see it, you know exactly what it is that they're talking about. Okay, so that's the markings. So we talked about classification. We have a number of ways to identify different types of traffic. We have a number of different markings to use, each with different values. In general, the higher the value, the better the treatment it's going to get through the network. There are a few different exceptions, but in general, that's the way it's going to go. Another thing let's talk about is trust. This is something that was not on by default before, whereas in our switches, in our code, it is enabled. So what is trust? Well, trust is a way to preserve markings once they're already on traffic. Otherwise, without trust, every single time a packet comes in to the switch, we would have to look at it, classify it, regardless, and then apply our own markings. What we do with trust is we honor the existing markings that come into a switch. So let's say I have a phone, and this phone is sending traffic with a Dscp of 46 and a Qos of 5. So a standard phone has both layer 3 and layer 2 markings on it. And so we'll get both of these markings, and that's fine. So by default, now we trust those markings. And if we trust them, all that means is that as the traffic comes in, unless we do something explicitly to alter this, the traffic will leave the switch with the same markings that it came in with. And this assumes that these are trunks, obviously. Otherwise, without a trunk, we wouldn't have Qos. We would just keep the Dscp and the Qos would disappear. So that's with trust. And again, by default, on every single port, we trust markings in this code. This is different than what you might be used to if you come from a V2 background or on different types of switches like 3750s or some of the other Catalyst switches that don't run this IOXXE code. Now, we don't have to trust. In our switches, we can actually set up conditional trust. So I'll only trust it if I see something specific on the other side, like a phone. So I could configure the trust to say, if there's a phone on the other side of this port, trust it. Then we'll trust the markings. But if it's not a phone, then we won't trust it. So let's pretend that that's how we said it. We said trust only if it's a phone. Okay, now it's a conditional trust. So let's pretend that this wasn't a phone anymore. Let's just say it was a PC. And it's running, at this point, if it's a PC, probably don't have Qos, but we still have Dscp. And we'll pretend that it's running, Jabber, and Jabber is configured to mark the audio traffic with a Dscp of 46. Well, okay, now that we have a conditional trust, what'll happen is the traffic, the switch will analyze what's on the port. And usually it uses CDP to try to figure this out. It'll realize that this is not a phone, and so it will sort of note this as untrusted because I don't see the device that I want to see on the end. So as the packet of Dscp 46 comes into the switch port, since we don't trust it, we're not seeing the device that we want, we are going to blow that away, and as we send it out, we just wipe it out and set it back to the 0 marking. And that way, if we don't trust it, we don't want to honor its markings. We're just going to blow those away. Or we could create a policy that says, you know what, I'm not going to trust what you mark it as. I'm going to analyze the traffic and I'll put my own markings on it. But without a trust, either we're wiping out the markings or we're responsible for setting our own markings using some form of a policy. If at a later date someone unplugged this PC, put a phone in there, at that point we would detect the phone, and now we would trust it again, and then we would allow that 46 to flow across unchanged. So that's what trust is going to give us. We're just going to honor the markings as they come in, send them through the switch, and they're the same markings as they leave as they were when they came in, unless we explicitly make a change through some sort of other policy. And just remember that we trust by default now. In order to untrust a port, we have to do some form of a conditional trust and not see what it is we're trying to see. So that's the concept of trust. The concepts we've talked about up until this point are probably all you're going to need to worry about on the wired side of things. We're mainly concerned with classification and marking and making sure that we trust as appropriate. Now we have other things that we can definitely do with QoS. I believe most of these other things that we talk about will show up mainly in the wireless side of things. We're generally asked to do a little bit more on the wireless side than we are for the wired side because this exam isn't about making us be wired QoS wizards. Yes, we should know our stuff on the wireless side, but on the wired, it's mainly just make sure that those markings are there and we'll let the route switch guys deal with the more advanced policies, I guess. But let's just talk about the other types of things we can do with QoS, just so that you're familiar with them. Another thing that we can do with QoS is prioritization, which kind of goes along with queuing. If I even spelled that right. I think there's an extra E in there. Yeah, I think that might be right. Prioritization and queuing. This says, how do we treat the traffic? And this typically comes after we've classified the traffic. You know, maybe it's based off of its markings. And oftentimes what happens is the marking determines what sort of treatment it gets in terms of prioritization and queuing. So our switches have, on the wired ports, 8 queues, and up to 2 can be priority queues. We don't have to make them priority queues, but we can have up to 2 different priority queues of the 8 overall queues. With the wireless side, we don't have 8, so we're talking strictly wired ports here. And the priority that we do is strict priority queues, which means we have 2 levels of priority, priority 1 and priority 2, and then the rest of the stuff. And so as long as we have traffic in priority queue 1, we service that until it's empty. And then if that's empty, we can service everything in priority queue 2 until that's empty. And if that's empty, then we can start servicing the other queues as configured. And so very often, to prevent starvation, you know, if there was always something in queue 1 that could technically starve everything else out, we usually do things like policing or shaping to set a limit on how much that queue can do. So 8 queues, 2 priorities, and typically it's going to be the Dscp value. We'll send it to the appropriate queue, assuming we're talking about layer 3 traffic, which is typically what we're talking about here. So that's where the DSP value becomes important, because that's what's going to oftentimes send it to our different queues. Okay, we probably won't have to worry so much about prioritization on the wired side of things, but I guess there's always a slim sliver of chance. The good news is that when we start configuring policies, a lot of the policy configuration is applicable for both wired and wireless. So when we get into some of the things like prioritization on the wireless side, you can use some of that knowledge to do the similar types of things on the wired side. A few other things that we'll talk about, policing and shaping. Similar concepts, but just implemented a little bit different. Both of them are, the idea of both of them is to set a limit as to how much traffic can flow, you know, either out a queue or out an interface or whatever it is. And so maybe we have a 1 gigabit interface. And we have let's say we have a priority queue. So we'll say priority queue 1. We don't want to just let priority queue 1 eat up all 1 gigabit of our interface. You know, if we're oversubscribed, this is really where we're coming into play. We don't want priority queue 1 to get everything. We want to leave room for some other people. And so you might do some policing or shaping. And so you might say, you know what, let's police this at 100 megabits per second. And so what policing does is it sets a hard limit. And so as long as traffic is in this queue, priority queue 1 in this case, is below the police limit, which is 100 megabits a second at the moment, that traffic continues to flow. But once we bump up to 100, going above that, we're exceeding the police. So if we're below it, the traffic below the limit is called conforming traffic. The traffic above the limit is called exceeding traffic. And so when we exceed the limit for policing, we can do one of two main things. We can just drop it. So anything above 100 megabits a second, boom, you're dropped, and that's the end of it. Or what we can do is we can remark it down. And typically what remarking it down would do would be to send that traffic to a different queue. And then the other queue, which might have other things to contend with down there. So it's a way of not dropping the traffic, but at least lowering the levels a little bit to a little bit more reasonable level. I'm guessing most of the time in our lab, we would probably be doing this more on the wireless side, but we would probably be dropping it more often than not. So we just have that hard limit, and then we just say what we want to do with exceeding traffic, either drop it or mark it down, and that's kind of the end of it. Whereas shaping allows you to, we're still setting a limit, so we could still set a limit of 100 megabits a second, but what we do with shaping is, so if we have traffic going above the limit, what we do is we sort of hold it back a little bit, and we'll buffer it. And so we'll still send the traffic out at 100 megabits a second, and all the extra traffic we'll hold in a buffer, hoping that the traffic coming behind it slows down, and then as we have room, we'll empty out the buffer, and we kept it at the 100 megabit limit, but we didn't have to drop anything. Now eventually, if the incoming traffic is averaging more than 100 megabits a second, that buffer will run out, and then we have to drop it at some point, right? But we try to, with that buffering, not have to lose any packets, kind of a deal. So we're still setting some sort of a hard limit, but policing typically involves dropping, whereas shaping tries to prevent that drop behavior. And another thing with policing and shaping is oftentimes you're limited to what you can do based off of which direction. We can usually shape in an outbound, so as I send traffic out, I can shape it because I can store stuff in buffers, but I can't shape traffic coming inbound because I can't. So I can police on the inbound, I can police on the outbound, but I can really usually only shape in the outbound direction. So that's policing and shaping. Those are the main concepts of QoS in general, things that we could do on our switches. We're probably, again, not worrying so much about policing and shaping on the wired side of things, or queuing prioritization on the wired side of things, but absolutely classification and marking. So to go along with classification and marking, talk about one last thing here in this video before we actually start configuring things in the next video, and that is standard voice markings and protocols as well. So we'll start with the markings. When we write policies, again, very often our policies are surrounding voice, and actually I'm going to include video in this as well. Voice and video traffic. And by and large, voice and video has fairly standardized markings that we can expect, whether it's in Dscp or in Qos. And so it's good to just know those, just so that you're familiar with them. So let's talk about first voice. Voice, again, voice has two main components. We have the audio stream that actually carries the voice sounds, and then we also have voice call control. This is what's used to set up the phone calls, tear down the phone calls. It's usually in between the phone and something like a call manager. And so, call control is what says to the phone, hey, start ringing, someone wants to talk to you. And when you pick it up, call control tells the other side, hey, he picked up, let's start sending the audio, kind of deal. And then on the video side, we have the video. And we might have video call control as well. Think of something like Jabber that can do video or audio. And so if I want to set up a video call, there's call control with that too. So we'll talk about these. What are my standard markings for these? Well, we'll do Dscp, and we'll also do Qos. Those are our two main markings that we deal with. So voice audio, we use 46 or expedited forwarding if you want to talk per hop behaviors, and a Qos of 5. This is every time. This is our standard voice audio marking across anything that ever does voice. This is what it should be using. This is the marking for voice. For call control, we should be using a Dscp of 24, also known as class selector 3, or a Qos of 3. Now, this value right here, the Dscp value of call control, has changed in the past at certain times. If you look at some old documents, you might see reference to call control using a marking of Dscp 26 or AF31. That marking should have gone away a while back. If you look at the current QoS SRND guides, anything in fairly recent history, I mean like 3, 4, 5 years, probably even a little bit more back, we should be standardized on 24, but it is still very common to see in documents that are honestly not super old that they talk about a Dscp of 26. So everything we should be doing is 24 unless explicitly told otherwise. If they say call control uses 26, fine. Build your policies around 26, but I would assume 24 unless explicitly told otherwise. This is pretty standardized by now. Video, most often from my experience here, the Dscp is going to be 34 or AF41 and a Qos of 4. Fairly standard video marking there. You might see a CS4. I've seen some where like streaming video gets a little bit different marking than like two-way like video conferencing type video, whether it's a one-way streaming video or if it's a two-way video conferencing video. Again, if they tell you something different, you go with what they tell you, but this is a fairly standardized marking, something that you would see, I believe, with like Jabber, if you're doing video with Jabber. Call control, I believe, should just be the same. Assume 24, CS3 with a Qos of 3. So these are kind of fairly standardized markings for our voice and video traffic. Not bad to have kind of committed to memory, but more often than not, they'll call these out in the lab. And then I want to talk about the protocols so that you can, if need be, write an ACL to match this type of traffic for our classification purposes. So let's talk about, we'll mainly just talk about voice protocols. So our audio protocol is called RTP, or real-time protocol. This is the protocol that we use for all of our voice audio. This is a UDP application, and we use a range of ports, 16,384 through 32,767. Very big range of ports. 3267 is 2 times 16,384 minus 1. So if you can remember 1, either just have it or double it. And you've got kind of the other number there. So UDP, this range of ports, and actually both ends should use these range of ports. RTP is phone to phone. So this is a direct session between phone A calling phone B. They're talking directly to each other with this RDP. And so as you write ACLs, if they wanted to limit, your ACL to the voice VLANs, if there were voice VLANs, then yes, you would. It would be from one voice VLAN to another voice VLAN. Although since we're using Jabber, the concept of voice VLANs is kind of falling away. Everything's just sort of converging onto one now. But it is phone to phone, or endpoint to endpoint. If it was Jabber, it could be PC to PC, whatever it is. From a call control perspective, we really have two that we might see. Since we are using Jabber, my guess is they're going to be more calling out SIP. I think it's Session Initiation Protocol. SIP could be UDP or TCP. I think Cisco more uses TCP, if I remember right, but it could be UDP or TCP. And its ports, oops, sorry. Let's try that one again. Hit a button accidentally there. 5060 through 5061 are standard ports. So TCP or UDP ports 5060 through 5061. And this should be from the phone or the endpoint, your Jabber client, to a call manager of some sorts. So in our racks that we have a router running Call Manager Express. And so my SIP client would talk SIP to the Call Manager Express router to initiate any phone calls or realize that someone else is trying to call it, whatever that might be. And so the call manager or call control device should be listening on 5060, 5061, UDP, or TCP. So they might narrow this down. Maybe they say only worry about TCP 5060 or something like that. But if they just get generic about SIP, cover your bases, cover both protocols with both ports on both sides. And the call manager for sure will be using this. I believe I've seen that the phone might also use the same port in its conversations, but oftentimes you could just write this with 5060, 5061 on the call manager and just let the phone just be sort of an any port. The other call control that we might have, since we're talking Cisco type stuff, is Sccp, or you might hear it referred to as skinny protocol. This is what historically, all Cisco phones use. Now a lot of Cisco phones are now being able to move over to SIP, and SIP is becoming a lot more of the standard nowadays, but you still might run into it in the lab. And if this is the case, this is TCP, port 2000 on the call manager. And again, like SIP, this is between the phone or the endpoint to the call manager. So all call control that we care about is always between the phone or the endpoint and the call control device. And so the call manager would be listening on port TCP 2000. So as you write an ACL, it would say TCP port 2000 on the call manager from the phone on any port kind of deal. So those are our standard voice protocols that we might see, probably SIP over Sccp now in this version of the lab. These are the protocols that they use between TCP, UDP, and the port ranges that they would use, and this is the traffic flows, whether it's RTP, which is endpoint to endpoint or phone to phone, where the call control is endpoint to call manager. So hopefully that gives you a decent overview of QoS on the wired side. Hopefully it equips you for what we're going to be doing in the next video, where we actually get into the configurations to make the parts of this stuff work.